Okay, the last thing we're going to go through today is flipping, stretching, and compressing quadratic equations. Alright, in the last two videos we've shown you exactly how to draw the original one, y equals x squared. So we're just going to quickly plot those points so we know exactly where they are at 1 and 1, 2 and 4, and 3 and 9. So, we have our original one, y equals x squared. Now, we're going to talk about the variable a. And in that case, we're talking about the coefficient in front of the x squared, okay? So if you get a number in front, depending on what that number is, it's going to change this parabola, okay? The first thing we're going to do, if you notice, technically there's a number 1 in front of this right now, okay? Is it positive or negative? Positive, good. So since that 1 is a positive term, this parabola is opening upwards, okay? We're going to take that exact same equation, we'll do it in red. Y is equal to negative x squared. And all that's going to do is our vertex is not going to move. It's going to stay in the exact same spot. The only difference is we're going to go over 1. Instead of going up, we go in a negative direction, we go down 1. Okay? Same idea. Instead of going up, going over 2 and up 4, we go over 2, down 4. So it is the mirror image of the parabola we had above, except that is now opening downward. So the first thing you need to remember about A, and if A is positive, opens up. If A is a negative term, it opens downwards. Okay? Very important to remember, because on top of those positive and negative terms, what we're going to be doing is we're going to be putting numbers in for A. Now, depending if A is greater than 1 or less than 1, it's going to change the shape of this parabola. So let's do an example where we have y is equal to, and in this case we'll do 2x squared. So in this case, is A greater or less than 1? Good. I'm glad you guys know how to count. So it's greater than 1, which means what's going to happen to this parabola is going to be stretched. So think of it like an elastic band. It's going to be pulled from the top. So if we had a round elastic band, oops, I forgot about that. Okay, let's try it again. If we had a round elastic band, nuts. And we pulled it from the top to the bottom, it would go thinner like that. Okay? So what that means, and now this is the tough part about calculating this. From the vertex, normally we go over 1, up 1. What we would normally go up by, we need to now multiply by this coefficient. Okay? So this idea is a little difficult. I'm going to try to calculate it on the side for you. So normally we go over 1. 1 squared is 1. Okay? So we'd go up 1. I now take that 1. What is 1 times 2 going to give us? 2. So instead of going over 1, up 1, we go over 1, up 2. Okay? Doesn't seem that hard so far. Same idea with negative 1. Negative 1 squared is positive 1. And positive 1 times 2 is 2 units. So we'd go up 2 again. Now, this is where it gets a little trickier. 2x squared. Yeah, still 2. Yeah, we're still talking about 2x squared. In our next example, we would normally go over 2. Well, 2 squared, right? And there's a 2 in front here. 2 squared is what? 4. Now we have to take 4 and multiply it by 2. What are we going to get? 8. So instead of going over 2 up 4, we essentially double it. We multiply 2 times 4. We need to go up 8 units. And what you're going to notice is this parabola is much thinner, even though I didn't draw it perfectly, is thinner than the previous parabola we had. Okay? So think of it like an elastic band. It's been pulled. It's more to the inside of our original one, which is drawn in black. That same idea, so if A, we'll write this rule down, if A is greater than 1, then we stretch. TCH? Yeah. Okay? Oh, there shouldn't be an equal sign there. Just say A greater than 1. Now, the other instance, we don't say A is less than 1 because when A is less than 1, it's negative and then it turns downwards. We're looking for when the A value is actually between. If you guys remember that domain range, we're looking for when A is greater than 0 but less than 1. And then we're going to have what's called a compression. Now, I know the compression idea looks odd. You might think that it's compressed from the inside, this one here, that's technically been stretched. But I want you to always think of we're doing everything from the top. So if we pulled it, okay, our a got greater, it got stretched, it became thinner. Now think of it as if there's a ceiling and it's coming down on the original parabola. It's going to compress it. This parabola is going to get wider and wider, as if something is squishing it. So let's make up another example here. Let's say we'll do y is equal to, you could have these in decimal or fraction form. I'm going to do it in fraction form. 1/4 x squared. So in this case, our a value is between 0 and 1. It's also known as 0.25. Okay? So we have to do the exact same thing we did before, but this time we have to multiply by 1/4, which is going to be a little different. So we start our vertex here. It's still going to be the exact same spot. So as long as there's no h and k involved, vertex is always at the origin. We go over 1, up 1. What is 1 times 1/4? 1/4. So I actually don't go up a whole 1. I just go up a 1/4. Okay, so that's going to be roughly a 1/4. Now I go over 2. 2 squared is what? Okay, yeah. So we go over 2. 2 squared is 4. Now we've got to multiply it by this. So what's 4 times 1/4? 1. Okay? So we go over 2, and we only go up 1. And if you're noticing already, this parabola is going to look much wider than before. 3 is going to give us a complicated number, so I'm just going to jump ahead to 4. 4, if we were to plug 4 in, so we go over 4 from the vertex, how many should we normally go up?
16.
16, good. But because we have to, that was what 4 squared would be, 16, and we got to multiply by our a term, which is a 4th. So what's 16 times 1/4? Anyone know? 4, good. So we go over 4, up 4. And if you notice, I'm not going to do all of them here, the points, but this is wider, or as the textbook calls it, compressed compared to the original parabola in black. These same rules apply for when it's negative. It will get thinner and wider depending if the number is greater than or less than 1. So we'll jump to that program and quickly show an example of this. Okay. So example of that would be, we did 2x as one of them. If you notice, the red parabola is thinner than the blue one. The other one we did, oops, we did 1/4, right? So 1 divided by 4. X. The green parabola is wider than that blue one we had originally. And we'll even apply those same rules. Don't worry about that. Let's say we had -7 x squared. If you notice, this parabola is heading downwards and is much thinner than the blue one we had before because the value is much greater than 1. And then we'll do another. I know it looks cool. We'll make a number very small here. We'll say it's 1/20th. Okay, 1/20th x squared. And I want to make it negative. You'll notice that parabola, and we'll try to zoom out, is much wider than all of those original ones, okay? Because the farther we get away from 1, or closer to 0 we get, the wider it's going to get. And vice versa, the larger or higher we get away from from 1, the thinner this parabola is going to get.